Right, the next section is about oxidation of alkenes. In Gen Chem, you learned that oxidation meant loss of electrons, right? You remember doing oil rig? You remember oil rig? Oil meaning oxidation is loss. The rig, RIG, is reduction, is the gain in electrons. That's what you learned in Gen Chem, and you had to do all these problems about trying to figure out where you're gaining electrons and losing electrons. Well, in carbon, basically oxidation means gain of oxygen. Okay, so oxidation means gain of oxygen. And reduction in organic chemistry means loss of oxygen. Very simple. It's just the number of bonds to oxygen. The more bonds to oxygen, the more oxidized it is. The less bonds to oxygen, the less oxidized, or the more reduced it is. That's plain and simple. That's all it is. Okay? The first reaction we're going to talk about in this section is called epoxidation. We've talked about what an epoxide is in class already. If we have not, we're going to talk about it right here. But an epoxidation, remember, an epoxide is a three-membered ring with an oxygen as one of the atoms. All right, that's an epoxidate or an epoxide. That's the functional group epoxide. Okay, I had a student once call it a martini. I'll show you kind of the cute little thing, but it looks like a martini. So she. Anyways, an epoxide is two carbons. So you have two carbons here. That is, it's a three-member cyclical ring with an oxygen. And very useful. You've probably heard of epoxy resins. Epoxy resins come from epoxides. It's basically a polymer of epoxides. All right, so epoxides are used a lot. They are a little strained, but they are stable enough to actually be formed. So let's talk about an epoxide and how you make it. Again, we're going to start with a double bond. Now, the reagent is a oxidized form of a carboxylic acid. It's what's called a peroxy acid. Peroxy acid is what you use. And it's just a really overly oxidized form of carboxylic acid. It's an carboxylic acid with two oxygens. That's what you use. It's called a peroxy acid. All right. Now, your book has three different ways as to how they do this. I don't like how your book does it. I wish they would just pick one instead of three different ways. But they might show it as RC-O-O-O-H or as RCO3H. All right. Or the actual reagent that people use is called MCPBA. All right. Now, it is a lowercase m, capital CPBA. And that word, it stands for metachloro peroxybenzoic acid. Benzoic acid. All right. The structure, you do not need to know the structure. All right. You just need to know the word MCPBA, or just know that it's basically some sort of highly oxidized carboxylic acid. And that's it. So you take your double bond, add MCPBA, and you form your epoxide. Now, as far as your MCPBA, people always like to know what happens to it. It's not part of the final product. I usually don't write what happens to the other stuff because you usually purify that away. All right, it's not important. That's not the important part. The epoxide is what's important. But what basically happens is this MCPBA becomes MCBA. Becomes MCBA, metachlorobenzoic acid. It loses the extra oxygen. That extra oxygen gets attached onto your epoxide. But this is not important. I don't care what happens to that. All right? This is the reaction. You take a double bond, add MCPBA, or you might see this over the arrow, or you might see them write it as this, and you can oxidize to form the epoxide. Okay? Now, let me just show you a reaction that you can do with epoxides. You might be thinking, all right, I got an epoxide, but what can I do with it? This is just a second reaction. You can add acid and water to this. Okay? And what you form is a diol. Diol is exactly how it sounds. Diol. Di meaning two, OL meaning an alcohol. So it's two OH groups on your same compound. It is a trans addition. All right, same type of thing. The mechanism is in the book, but I can go over it real quick. You have your epoxide. All right. Acid protonates your epoxide. It gives this oxygen a positive charge. So already this oxygen is very strained. When you put a positive charge there, it strains it even more. So water now can come in opposite. So it's just like the mechanism of the halogenation, all right, of the halogen reaction. It's coming anti because of the three-membered ring. Anytime you get a three-membered ring intermediate, you're going to get an anti-addition. And then another water molecule comes in and plucks out that hydrogen, just like how we saw in the hydration mechanism. So you kind of see a lot of the similar types of steps and mechanisms depending on what you have. All right. So just to show how this gives you the cis product, first reaction is MCPBA to form the epoxide. That's just how to make an epoxide. This second step is just another reaction that you can do with it. Adding your acid and water. Oh, I'm sorry, this is incorrect. This should be an epoxide. Your double bond is gone. Sorry about that. So this is what it should look like. All right. Then you add acid and water, and so let's kind of put this wedged so it's coming out towards you. So add acid and water, and you get an OH on this side and the oxygen opposite to it. Okay? The second reaction we're going to learn about is, let me see what I put it as, hydroxylation. Hydroxylation. That's fine. All right. In particular, it's called dihydroxylation. I should have written that first. It's exactly as it sounds. You're going to add. You're basically making a diol, just like the other one, but this time you're going to make a cis diol. This is a way to make cis diols. The previous section I showed you how to make a trans diol, but it has to go through the epoxide. Okay, the reagents are KMNO4. It's a very strong oxidizing agent, and this is done in sodium hydroxide. All right, it's very important you realize it's in sodium hydroxide because there's going to be another reaction which you do in acid, and it does a different reaction. And what you make is a cis diol. You've already learned what a diol is. You learned the trans diol, but this makes cis diols. Alright, so again, let's use my trusty cyclohexene because this shows you that it's not going to rotate KMNO4. And sodium hydroxide. OH. People like to know what happens to the MnO4. It turns into MnO2. Now again, you do not need to know this. MnO2. All right. The magnesium gets reduced. Why is it getting reduced? Because you're losing what? You're losing oxygens. All right. What's happening to your alkene? You're gaining oxygen, so that gets oxidized. All right. As far as the potassium, that kind of gets hooked on extra hydroxides and oxygens and all the other stuff. Again, spectator ions. I don't care about it. Okay, if you're just so curious, if you want to know, there it is, but I'm not going to ask you anything about it. You will not need to know about it. Because, remember, this class is organic chemistry. It's about carbon, not about manganese. Okay? So that is a dihydroxylation. That is basically it. That's the whole reaction. So let's now talk about the third reaction. This is going to take a little bit more time. This is oxidative cleavage. And it's exactly how it sounds. You're going to cleave your double bond in this case. All right? You're going to actually break the double bond in half. Now, there are three possible products, and in all variations of these three possible products. All right? Your products can either be a ketone, it can be a carboxylic acid, or it can be CO2. These are the three possible products you can form. It all depends on the substitution of your double bond. Substitution of double bond. Okay? If your carbon on the double bond, is a di-substituted, it will form the ketone. If it's mono-substituted, now this is each of the carbons on your double bond. Now I will show you examples. I'll just give you the rules. That will give you the carboxylic acid. and if you have no substitution, so you just have two hydrogens on it, no substitution, you get CO2. Okay, so those are basically the rules. Okay, so let me just show you examples. Okay, we're going to put R groups. All right. Now, notice, and again, and your reagents, sorry I didn't talk about your reagents, this time it's KMNO4, but this time it's in hot acid. You need to heat this up. So this is in hot acid. Notice, now we're just looking at each carbon. This carbon right here has one R group and one R group, so it's di-substituted. This carbon has an R group, and it has a second R group. That's also di-substituted. Now, I know that the one is tetra-substituted. We talked about this in a different chapter, but your frame of reference at this point is just looking at each carbon. I've got two R groups on it. This carbon has two R groups on it. Therefore, since each carbon is di-substituted, they're both going to make a ketone. So this reaction breaks your double bond, and it puts an oxygen where in place of that double bond. So you still have a double bond, but instead of the other carbon, you have an oxygen. And it splits the molecule in half. So you technically form two products, because it breaks it in half. And because these are R groups, here are your R groups, you get the ketone. Okay? Now what happens if you have one R group, and it doesn't matter if it's cis or trans, it has no bearing on it whatsoever. Notice this time, this carbon only has one R group, so it's monosubstituted. This carbon only has one R group, it's monosubstituted. So if you add KMNO4 and acid and heat, you now get the carboxylic acid. So that hydrogen, you get an oxygen in there, and you still have your R group. All right, so this carbon, let's call that carbon A, is carbon A. This R group, let's call it R sub A, that's R sub A. And then let's call this B, let's call this R sub B. So I wish I had colors. I don't think LiveScribe has colors yet, but maybe in the future I'll be able to do it. Oh, I'm sorry, that becomes a carboxylic acid, OH. Alright, so in this case you get the diacid. Now you might be thinking, what happens if one of the carbons is di-substituted and the other carbon is monosubstituted? Well, follow the rules. One of your products becomes a ketone, the other product becomes a carboxylic acid. So let's look at an example. Let's say you have CRR, double bond to CRH. Alright, why don't you take a second, put it on pause, and write what the product should be. Alright, the product should be, you should have one of your carbon on the left should be the ketone. The carbon on the right is going to be carboxylic acid. There is nothing special about it. Alright? This carbon is di-substituted, so it becomes a ketone. This carbon is monosubstituted, it becomes a carboxylic acid. Alright? Simple as that. Now what happens if you have no substitution? So let's say you have a carbon with two hydrogens, and the other carbon, let's say, has an RH on it. Alright? Well, the one with the RH, we know what happens to that. That becomes a... I obviously don't know what you said, but I'm assuming you said it correctly. Becomes a carboxylic acid. And what happens to the carbon with no substitutions? Hydrogen, remember, does not count as a substitution. All right. Well, if you look back, you'll see on the third, or C, was if you have no substitutions, it becomes CO2. That carbon turns into CO2 gas. That's a gas, and it goes off into the atmosphere. Okay. And then you can have all types of variations. So let's do a few practice problems. Okay. Let's say you have that one. And that one. Alright, we'll do skeletal structures. KMNO4 in acid. And let's do KMNO4 in acid. Put it on pause, write the products. Alright, I wrote them out for you. These should be what your products are. On the first one, you're cleaving right here. Notice you have 1, 2, 3 carbons. Notice there's a hydrogen here. Alright. So you have 1, 2, 3 carbons. 1, 2, 3. So because this is monosubstituted, this becomes a carboxylic acid. That corresponds to that one. The next one, this one, you have a di-substituted. So you have a CH3, carbonyl, CH3. So you form the ketone. Down below, notice this carbon right here has 2 hydrogens on it, so it's there's no substitution, so that becomes the CO2, and this other piece, 1, 2, 3 carbons long, becomes a 3-carbon carboxylic acid because it's monosubstituted, because there is a hydrogen right there.